Hello everyone, thank you for joining me. Before I start the next video series, which we will cover OSPF, I thought I'd take a moment and talk about OSPF link types. It's important to understand link types in OSPF for the following reason. You'll hear me say a lot that OSPF has the ability to interpret the interface it's configured on. Example, OSPF interprets an Ethernet connection as a broadcast network, because that is how most LAN networks are built. But we know as network engineers that the telecommunication industry has advanced over the years, and Ethernet connections are now being deployed as the connection of choice over long distances. Today, most point-to-point connections between two sites over two different geographical locations are implemented via an Ethernet connection. This causes a bit of an issue, and we'll go over it in this video. So over here on the left, you'll see that I've connected 5 routers to this switch. 5 routers to the switch. By default, this allows all routers connected to the switch to pertain to the same subnet or same broadcast domain. Now, if you take a look at the IP address of 10.1.1.0/24, this is the IP address that I have dedicated to this particular broadcast domain. If you look at the configuration, for example, I have also associated the appropriate IP address with the corresponding router. So 10.1.1.0/24, I've given the .1 to router 1, .2 to router 2, and .3 to router 3, and so forth. Okay? If you look at the subnet mask is also reflective of the /24 subnet, which means that they are all participating in the same broadcast domain. If we move forward and review the OSPF configuration for a moment, you can see that the network command is replicated on all interfaces that pertain to that subnet as well. With the appropriate area that has been defined. This is the appropriate configuration under the circumstance and use case as OSPF, because all the routers are connected to the switch and all routers pertain to the same subnet. Now, OSPF understands that because all routers in this broadcast domain can see each other, but this causes a problem. Because under traditional circumstances, router 1, for example, would have to create a one-to-one relationship with router 2, router 3, router 4, and router 5. This holds true for router 2, would have to create a relationship with router 1, router 3, router 4, and router 5. And router 3 would do the exact same thing, and so on and so on. You can see that the amount of adjacencies, the amount of maintenance that the OSPF protocol would have to undertake increases as the broadcast domain gets larger. As the broadcast domain gets larger, the database tables get larger, the routing tables get larger, and therefore convergence time is also affected. Okay? So OSPF mitigates this constraint by electing a designated router and a backup designated router for these types of circumstances in broadcast networks. Now, how does OSPF accomplish this task? How does it elect a designated router, a backup designated router? Well, as soon as it's recognized that it's participating in a broadcast network, so all it takes is for OSPF to be configured on an Ethernet interface, it goes out and tries to select, or participate rather, in an election process. So once the routers all recognize that they are sharing the same subnet, the election process begins, and the router with the highest OSPF priority will become the designated router. And by default, all routers have a priority of 1. If the priorities of the links are all the same, the router with the highest router ID wins the election. The router with the second highest priority or highest router ID will become the backup designated router. So let's go ahead, apply this configuration, and see how the election process takes place. All right, so I've just applied the configuration, and let's go take a look. So if I go on to router 1, for example, which is supposed to be my designated router, because that's what I'd like it to be in my design, I see that that's not the case, and we'll analyze why. So show IP OSPF neighbor will tell us the neighborships that I have, and most importantly, the states that they're in. So currently on router 1, it has a two-way DR other or druther, which means that the relationship that router 1 has with router 2 is neither a relationship of between a designated router and a backup designated router. If you look at the relationship with router 4, for example, you can see that it's in a full state relationship and that router 4 is considered the backup designated router. Same thing goes with router 5. Its relationship with router 5 is in a full state, and in this broadcast domain, it looks like router 5 has been elected to be the designated router for this broadcast domain. So the question is, why? Why did that happen? Well, like we said, right, as soon as OSPF recognizes that it's connected to a broadcast network, once the routers all recognize this, that they're sharing the same subnet, the election process begins, and the router with the highest priority will become the designated router. Now, like I mentioned before, the default for all OSPF speaking interfaces is 1, unless it's been statically and manually defined. So all things kept equal, if the priority of the links are the same, the router with the highest router ID wins the election process. And because 5 has a router ID or loopback address of 5.5.5.5, he automatically wins the election process and becomes the designated router. And hence, router 4, who has the second highest, wins the backup designated router. So it's the president and vice president of this broadcast domain. We have to keep in mind the reason OSPF defines these relationships the way they do. And the reason is because OSPF is trying to mitigate the constraints of scalability within a broadcast network as defined earlier. Now, the two-way state means that router 1 has received a hello packet from router 2 and router 3 and sees its own IP address in the hello update. Now, the routers reach a two-way state once this happens. The full state means that the relationship is completely converged and synchronized, meaning that the databases are completely succinct with each other at this point. Now, once the routers in this broadcast domain have completed their election process, they need to begin building their topology tables. This is achieved by each non-designated and backup designated router, so in this case router 1, router 2, and router 3, exchanging information only with the designated router and backup designated router. So router 1 will only send topology information to router 5 and router 4 under this scenario. The designated router and backup designated router will in turn redistribute that topology information back down to router 1, router 2, and router 3 to begin building its topology table. Now, how does this happen? How does this all work? Well, it happens by every non-designated router and non-backup designated router sending topology information directly on the multicast address 224.0.0.6. You see, once the election process is complete and we have the designated router and backup designated router defined, these are the only two routers that are allowed to listen on that multicast address. So all the non-designated routers and non-backup designated routers send their topology information to that multicast address because they know that the real designated and the real backup designated router are the only ones listening on that multicast address. Once the designated and backup designated router collect all that topology information, it then announces out downstream to every other router in the subnet on the multicast address 224.0.0.5. And this is how they build the topology database and how they mitigate the constraints of scalability in a broadcast network. Okay, so let's go ahead and perform the show IP OSPF database. And as we can see, there are LSA type 1 packets, and LSA type 1 packets are packets that are intra-area, so updates that pertain to the area itself, okay? The LSA type 2 packets only exist when there's a designated router and a backup designated router election process, okay? Very important. Now, for all intensive purposes, we have a situation in which we have allowed this broadcast domain to be equal in every part. And as a result, it's selected the designated router as router 5 and the backup designated router as router 4. Now, that was not our intention. Our intention is to have router 1 as the DR and router 2 as the BDR. So what I'd like to do is just show you how we can effectively manipulate the election process. And we do this by going config T interface gigabit Ethernet 00, and under the interface you do show IP OSPF priority. And remember, the higher the priority, the better the election. So the higher the priority, the better it is. So if you go config T, interface gigabit Ethernet 00, IP OSPF priority, and I'm going to put 10, knowing that all the other links are 1 because that's the default. All right, and I'm going to go on router 4, and I'm going to go clear IP OSPF process, like that, and I'm going to go clear IP OSPF process on router 5, and you have to because they were effectively the chosen designated router and backup designated router when everything was kept equal. So let's just take a look now and see the neighborship. Show IP OSPF neighbors. Okay, so this one's still in the extract state. Okay, so if I go to router 5, we can see that it has a two-way with router 3 and router 4, and router 1 and router 2 are now effectively exactly the way we want our topology to look, where router 1 is the designated router and router 2 are the backup designated router. So that is the way you can have more control over the election process in your broadcast domain. Okay? Up until this point, we talked about OSPF in a broadcast network, but I'd like to talk about OSPF in a point-to-point topology as well. So let's take a look at the scenario that I've created. Now, all the routers in this particular topology are not connected to a switch, but rather they're connected directly to each other. They have a point-to-point relationship with each other. You can see that in the IP addresses as well. In the previous example, every single router was connected to a switch, and they all pertained to the much broader /24 network, meaning that they could reach every router that was on that subnet. In this particular example, I carved out 4 /30s out of this /24 network. So each and every router has a dedicated point-to-point connection with its peer. Okay? You see that in the configuration as well. So if we take a look at router 6, you can see that its gigabit Ethernet 00 interface is connected with .1, and its 01 interface is .5. Now, if we take a look at its counterparty, which would be router 7 in this particular example, you can see that router 7's 00 interface is matching up with router 6's 00 interface, and the subnet masks match as well. This is a subnet of a /30. Okay. Now, if we take a look at the OSPF configuration as well, you can see that the OSPF configuration is following that pattern as well. Both these routers have interfaces that pertain or are participating in the 10.1.1.0 network with the inverse mask of 3, and they're speaking in area 0. This rule is applied on all the routers. So what I'd like to do now is just apply the configuration, and I'll be right back. All right, so I just went ahead and configured the routers with the configuration that you see on your left, and we'll go ahead and take a look. So if we take a look at router 6 and I do a show IP OSPF neighbor, you can see that there is a full adjacency, which means that the databases are completely converged and succinct with each other. But we also see that even though this is a point-to-point link, that it has elected a designated router and backup designated router. So in this case, router 8 is a designated router because it did follow the election process on this particular broadcast medium, which happens to be Ethernet. Okay, and it went through this before. So to mitigate this situation, because essentially what happens is if you do show IP OSPF database, you'll notice that there are LSA type 1s and LSA type 2s. And remember, LSA type 2s are present only when there's a designated router and backup designated router. But the question we need to ask is it necessary? Is it necessary that OSPF create a designated and backup designated router under this circumstance when there are only 2 routers that make up this particular broadcast domain, which in essence is a point-to-point? Okay, it's a /30, and it doesn't. So to make OSPF work more efficiently in a point-to-point scenario, we would do show run interface gigabit Ethernet 00. All right, so take a look at that. So we're going to go into config T interface, gigabit Ethernet 00, and we're going to define the network as a point-to-point interconnection. And we're going to do that for all of them. Okay, we're going to go config T interface gigabit Ethernet 00 IP OSPF network type point-to-point. Okay, bear with me here really quickly. Okay, and last one. Okay, now this has reinstigated or reinstantiated a whole OSPF reconfiguration or re-adjacency establishment. So if we do a show IP OSPF neighbor, I can see that we are in a full state and that there is no election of a designated and backup designated router anymore, and that it is considered a point-to-point status, even though it's on a Ethernet connection. And the reason why that's also beneficial is if I do a show IP OSPF database, we have just eliminated the need for the LSA type 2 packet to coexist with the LSA type 1. I'm learning about the network, I'm learning about the topology databases directly from my neighbors, as opposed to having a designated router, a backup designated router, soliciting those updates on behalf. So it makes OSPF a lot more efficient. It makes OSPF work a lot better, and that's essentially what we're trying to do. And we're trying to lower the convergence time and lower the amount of packets that it takes for OSPF to synchronize its database. Okay, so I hope this clears up the different LSA types that we went through, and thank you for joining me.